Hi, so this video will be on our presentation for our assignment 2 on travel planner using Dijkstra algorithm. I'm Max and my group members are Sid, Antonio, Pamela, Vanessa and Linus. We are from group T15. So this is the scope of the presentation, and so we'll be moving on to the introduction first. So we developed a travel planner application that uses graph theory to model cities as vertices and connections as weighted edges for distance and cost. To find the most efficient routes, we implemented the bidirectional Dijkstra algorithm, which improves performance by searching from both start and end points. For accurate distance calculations, we utilized the Haversine formula and integrated an interactive map via leaflet.js for route visualization. With support from Dixit, we refine our algorithm and improve both the application's performance and user experience, resulting in a robust, user-friendly travel planning tool. So next, we'll be moving on to the interactions. So we'll be sharing about some key insights from our interaction with the chatbot, where we explored the topic of Dijkstra algorithm. To ensure our learning was comprehensive and well organized, we grouped our questions into 5 key sections: fundamentals, complexity and performance, real applications, limitations and alternatives, and finally, scalability and future innovations. Now I'll be passing my time to Linus to present on the selected questions from each section and explain why we asked it.
For fundamental questions, we ask, can you describe the step-by-step process involved in Dijkstra's algorithm for finding the shortest path in a weighted graph and explain the rule of each step? We ask this question because understanding the basics working of the algorithm is essential before diving into any technical discussion. The algorithm's logic from initializing distances using a priority queue to visiting nodes in order of distance forms the backbone of many routing systems today. Complexity and performance question, we ask, what is the time complexity of Dijkstra's algorithm when using an adjacency matrix versus an adjacency list, and how does the choice of graph representation affect its performance? This question was chosen because performance matters in real-world scenarios, especially for large data sets. We wanted to know how different graph representations affect the algorithm's efficiency. For the real-world application question, we asked, can you provide examples of real-world applications where Dijkstra algorithm is used, such as GPS navigation or network routing? We ask this to bridge the gap between theory and practice. It's one thing to understand algorithm academically, but it's another to see how it solves actual problems in industries like transportation and networking. For the limitation and alternatives, we ask, what does Dijkstra's algorithm fail when applied to graphs with negative edge weights, and what modifications or alternative algorithms can be used in such cases? This question was important because every algorithm has limitations, and understanding them prevents misuse. We wanted to know the conditions under which Dijkstra's algorithm breaks, and how other algorithms like Bellman-Ford or Johnson's algorithm can be used instead. Lastly, for the scalability and future innovation question, we ask, how does Dijkstra algorithm scale for applications like global transportation networks or large-scale IoT systems? As systems grow in scale and complexity, like global logistics or the Internet of Things, we're curious whether Dijkstra's algorithm could still perform efficiently. Next, we'll be evaluating the chatbot's response.
Hello everyone, today we'll be evaluating the explanation of the Dijkstra's algorithm across 4 key categories. We'll focus on how well the responses addresses the fundamental aspects of the Dijkstra's algorithm, its applications, scalability, limitations, and the challenges it faces in real-world scenarios. So, first of all, let's start with accuracy. This category evaluates how correctly the content answers the questions. In the provided explanations, the chatbot accurately describes the Dijkstra's algorithm, including its core processes like node selection, distance updates, and the use of priority queues. For instance, it correctly identified that the Dijkstra fails when the negative edge weights are present because the algorithm assumes that once a node's shortest path is found, it won't be revisited. This is a critical point, and the chatbot addresses it well. Overall, the accuracy of the response is excellent. Next, for completeness, this category looks whether the responses cover all necessary aspects of the topic. Chatbot provides a solid overview of the Dijkstra's algorithm, its edge classes, and alternatives like Bellman-Ford for handling negative weights. It also mentions the role of priority queue and a backtracking process for reconstructing the shortest path. However, the response could go a bit further by discussing edge cases like dynamic graphs or how the Dijkstra's algorithm struggles with graphs that have rapidly changing edge weights. This will provide a more holistic view of the algorithm's limitations and applications. While the chatbot did touch on most critical points, additional information such as discussing other pathfinder algorithms such as A-star and the use of their real-time systems will enhance the completeness of the response. Our rate is very good, but it leaves room for more expansion. There's clarity, which measures how easy to understand the explanation. The chatbot responses are clear and structured, breaking down the steps of the Dijkstra's algorithm and its applications in a digestible way. For example, when explaining the agency matrix versus agency list, the time complexities are laid out in simple terms, making it easy to follow. However, some complex concepts showing how the priority queue selects the node with the smallest tentative distance will have helped users visualize the process better. In terms of clarity, the response is considered very good, but there's of course some improvement for simplified concepts. So this is done for my part, and Antonio will continue the rest of the evaluation.
Now, let's look at relevance. This category evaluates if the response stays focused on the topic and provides value. The chatbot remains highly relevant throughout the discussion, whether it's discussing Dijkstra's algorithm in real-world applications like GPS navigation or exploring its limitations with negative edge weights. The chatbot always stays on topic and provides valuable insights. For example, the mention of how Dijkstra's algorithm is used in logistic optimization is directly applicable to real-world problems. However, the chatbot could enhance the relevance by expanding on hybrid algorithms such as combining Dijkstra with heuristics for more efficient real-time pathfinding. Overall, the relevance is excellent, as the response consistently addresses the question with practical applications and avoid going off topic. To summarize, accuracy is excellent as the responses provide a correct and thorough explanation of Dijkstra's algorithm, covering their key concepts and applications. Completeness is very good, as all the essential points are covered, but a few areas could benefit from further detail, especially when discussing advanced algorithms. Clarity is very good, as the explanation is clear and easy to follow, but some of the more complex topics could be improved with diagrams or simplified language. Lastly, relevance is excellent, as the responses directly answers the questions and focuses on real-world users of Dijkstra's algorithm with insights into its strengths and limitations. This overall evaluation suggests the response is very well executed with just a few opportunities for expansion and clarification. Here are a few recommendations for improvement. First is to increase depth in real-world applications, particularly in real-time applications. Second is to provide visual aids to greatly enhance understanding. And lastly is to expand on alternative, as well as when they should be used over Dijkstra's algorithm. These enhancements would make the explanation even more robust and accessible. I hope this evaluation provides a solid understanding of how to improve algorithmic explanations and adapt them for different audiences and use cases. Next, we'll move on to the application.
I'm Pamela and I'll be talking about application. Here is what we prompted DeepSeek. We are building a travel planner app using Dijkstra algorithm to find the shortest path between cities. It needs to handle large data sets, calculate distances and fuel costs, and find alternative paths with intermediate stops. We requested a JavaScript implementation with optimizations like priority queues and Dijkstra algorithm for scalability. Next, we will assess DeepSeek's answer and make enhancements. DeepSeek's response effectively uses agency lists and the Haversine formula, but inaccurately stores latitude and longitude. Dijkstra algorithm is mostly correct, but sums distance and fuel cost inaccurately. Alternative paths use DFS but lack optimization. While optimizations like bidirectional, Dijkstra, and A-star are suggested, but their implementation is missing. Enhancements include correctly storing city data, fixing cost calculations, and improving path efficiency. This changes both accuracy, performance, and scalability for large-scale travel planning. Moving on to code implementation, the application uses two key data structures, a graph and a priority queue. The graph represents cities as vertices and connections as edges, stored in nested maps for efficient access. The priority queue implemented as a main heap ensures efficient node selection in Dijkstra algorithm. These structures enable scalable and efficient route calculations, making the travel planner application robust and user-friendly. The bidirectional Dijkstra algorithm improves efficiency by searching from both the start and end cities simultaneously. Step 1 uses two priority queues, one for forward search and one for backward search. Step 2, the algorithm explores neighbors in both directions, updating distances and priorities until the searches meet. This approach reduces the search space, making it faster and more efficient for finding the shortest path in large graphs. Step 3, the algorithm stops when the forward and backward searches meet in a common city. Step 4, path is then reconstructed by combining the forward and backward paths, ensuring no duplicates. This bidirectional approach significantly reduces completion time with a time complexity of O V plus E log V and space complexity of O V. It's highly efficient for medium-sized graphs, making it ideal for real-world route planning applications. Now I'll pass on my time to Vanessa to continue explaining about our code implementation.
Thank you, Pamela. I'm Vanessa, and I will be now talking about the formula used. The Haversine formula calculates the great circle distance between 2 points on Earth using their latitude and longitude. It accounts for the Earth's curvature, making it ideal for travel applications. The formula uses trigonometric functions to compute the distance, with Earth's radius as a constant. Here is the code implementation that calculates the distance in kilometers. Next will be the cost calculation. The cost of traveling between two cities is calculated using distance, fuel efficiency, and fuel price. The formula divides the distance by fuel efficiency to determine fuel consumption, then multiplies by fuel price to get the total cost. Here is the simple code implementation that the cost is in dollars. Next, I'll be showing the demo, which is our travel planner application. So here, you can see the HTML inside the Visual Studio Code and open with file server. So in here, we actually have total of 6 containers with 150 countries. So first, we're going to go from Paris, France to Berlin, Germany, and then we can calculate the route. So for the shortest path, to find the shortest path, we use bidirectional Dijkstra's algorithm. Export path, we actually use an additional feature, and we use an algorithm that is called DFS, which is the depth first search. So here you can see the different paths. Here's the path legend where it shows that the final best path is highlighted in green, and the second best path is highlighted in alternative path. You can see the difference that the best path only have 2 stations, and the distance duration and the cost is cheaper and faster. The second alternative path shown here, there are 3 stations, and the price, duration, and cost is a bit more expensive. So here only shows 3 explore paths, but if let's say the user were to click on others, they could see the other explore path that is shown in yellow. So whatever the user clicks on, it will show in yellow. So that is all what we have for our interactive map of the travel planner application. Next, I will be talking about the conclusion. So, in conclusion, we successfully implemented bidirectional Dijkstra's algorithm, provided multiple route options, and delivered an interactive map that is shown previously. We also enhanced from DeepSeek's response for better accuracy and usability. So in the future, we aim to explore A-star algorithm implementation and further UI or UX implementation. So that is all for our presentation as a team. Thank you.